Okay, well, again, I'm Eric Admin with the Sno-King Watershed Council, and welcome to our stream flow and habitat assessment class. So what we're going to go over this evening is talk about stream flow monitoring, what it is, why you do it, what are some different ways you do it, and what are the steps to doing it in the way that we're going to teach you. And then similarly, going to go over those same concepts with regard to habitat assessment. The information that I'm basing this on is there's a great document called the Streamkeeper's Field Guide. It's a reference book that you can get at Adopt a Stream. There's also some information from the EPA, and I'm also relying on Pierce Conservation District Stream Team training materials for this area. So first of all, let's talk about how stream flow and habitat relate to overall stream health. So there's a concept which is described in the Streamkeeper's Field Guide. It's called the 5 factors of biotic integrity. And so different things that are related to the biotic integrity or the health of a stream include water quality, like physical and chemical variables, also energy sources, otherwise known as like the food chain. What's happening in that food chain. So are there broken links? Like for instance, you need leaves to fall into the water, you need algae to grow, you need insects to feed on that, and then fish to eat that, and so on. So let's say you have some water pollution and you don't have enough of the stream bugs, you might have a gap in the chain. So that's another thing that can affect the overall stream health. The flow regime, in other words, how much volume and flows are over time, has a big impact, and we'll talk about some of the ways that impacts the stream health. Also, what sort of structures are present in the stream. So places for different things to live are really crucial. Some other things that we want to look at in terms of the habitat assessment is what's happening in the landscape, because that can affect the stream quite a bit. And also what's happening immediately around the stream. Does it still have some shading, or have the trees and the shrubs been cut down so that there's no shade? So those are some of the things that we're going to look at in terms of habitat and stream flow. So just covering some concepts of stream flow monitoring. What we're measuring essentially is the volume of water moving past a certain point over a particular period of time. And it's usually described in cubic feet per second. And what it's related to is how much water, primarily how much water is moving off the watershed into the stream channel, although it's also affected by groundwater sources. So some of the things that affect the stream flow, obviously weather. So if you look at the streams around here, when it's stormy, they tend to fill up really fast and get kind of, we call them flashy. The level of the stream goes up and the volume of water goes up pretty quickly. Some streams around here will go dry in the summertime and versus running more strongly in the wintertime. As we talked about, the land use will affect what's called the hydrologic cycle. Hydrologic cycle is essentially how water goes from the atmosphere to the earth to the land to water bodies and then back up into the atmosphere. And that happens a lot differently in an urban environment. Essentially, you get a lot more runoff and less groundwater recharge. So for instance, streams will, in an urban environment, the level will go up much more quickly in a stream and then drop down more quickly. Whereas in a more natural environment, the stream level will go up much more slowly and it will drop more slowly over time. So that can affect the groundwater recharge. And then also other things that people do in the landscape can affect aquifers and groundwater recharge. So flow can have some different effects. Flow is essentially, how much is flowing and how fast is it flowing. And so if you have too high a flow, you can get some things like scour. So that's something we see, for instance, in Swamp Creek. up and down the length of Swamp Creek. If you look at the banks, you can see that they've been eroded in some places down to kind of an underlying clay layer, and you get a lot of movement of rocks downstream. There's essentially a settling pond on Swamp Creek in Kenmore, and if you look at it, they periodically excavate out a bunch of rocks out of that cobble, and then over a period of time, it fills back up with rocks. So you can see that all this stuff's moving downstream, and that's related to high flow in the creek. And then the other thing that can happen with high flow is you get what's called turbidity, which is like the picture here. You get a lot of silt and a lack of water clarity. So flow also has an effect on what lives in the stream. So some things are adapted to faster moving water, and some things are adapted to more quiet water. As I mentioned, it affects the silt and the sediment that's carried, and then that will have downstream effects. And it also affects the level of dissolved oxygen. So for instance, on a faster moving stream, you might find a higher level of dissolved oxygen than you might say in the Sammamish River, which is kind of slow moving. So there's some different ways that you can measure flow. And one is with a fixed gauge that you've calibrated, and it's always in a given point. And so they've done some essentially taken some manual measurements to calibrate what sort of numbers this meter is, or this gauge is giving. And then over time, you can just have continuous data transmitted from this gauge. So this would be something that's done on like major waterways. USGS operates a bunch of these on different rivers. There's also handheld devices that you can use. And then the technique that we're going to be talking about is kind of the manual method, where you take some measurements by hand and then do some calculations and determine what the flow is. So in the method that we're doing, and in just any of these methods, there's an equation that defines how you quantify stream flow. So you figure out the average cross-sectional area of the stream, and then the length of the stream, and you multiply those by a coefficient that depends on the nature of the stream. So if you have a rocky bottom stream, essentially you have a smaller coefficient because you're going to have a little bit more, the flow is going to be slowed down a little bit more by the bottom compared to a smooth muddy bottom stream. And then time. So that's our basic equation that we're going to use to calculate stream flow. So the steps are, first, you want to get your equipment together, and there's a bunch of different things that you want. So essentially you need some string to make a couple of things called transects, where you're just making essentially a horizontal line across the stream that you can time an object moving across, and you can also measure the width of the stream there. You need some stakes to anchor it on both sides. You need something to pound them in. You need a tape measure to take some measurements. You need a measuring stick to measure the depth of the stream, and it's helpful to have it in feet and tenths of feet. So we have some measuring sticks that we've marked out in tenths of feet. You need something so you can mark intervals on the string or of the transect, so you can essentially set some even intervals to take your measurements. So you can use twist ties or clothespins or whatever works, or knots in the string. And you need something to use as a float. A lot of times people use an orange because it's sort of neutrally buoyant. It floats just a little bit like below the surface. So it kind of flows with the general water flow. Something to catch your orange, and something to time the time it takes for the orange to float between the two transects. And then something to do your equations. And finally, something to do your calculations and record your results. So gather up all those things, and then you're gonna figure out a stretch of the stream that is good for you to mark these transects. So typically you want to try to find a straight section, because what happens is if you have a bend, water's going to go faster on the outside of the bend and slower on the inside of the bend. So it's going to be hard to, unless you it's hard to pick where you want to drop your object to travel without going too fast or too slow. So a straight section is best. You want one that's deep enough. Basically, it's got to be deep enough that you don't have too much bottom effect, and also your object can proceed downstream without hitting the bottom, because that will obviously affect your timing. You don't want to find like a slow pool. So once you've picked your area, then you're going to use the stakes and the string, lay out your transects. You want to ideally make them 20 feet apart, but you can use whatever works. And then you're going to do some, so you've got your transects and your section of stream. Now what you're going to do is you're going to calculate your cross-sectional area. So here's an illustration. I think this is from the Streamkeeper's Field Guide. So we're going to essentially figure out what is the area of that cross-section of the stream. So first thing we're going to do is we're going to measure the length from bank to bank. So in our diagram, that's essentially roughly from point A to point E, although if A and E are not quite at the bank full width, you want to try to make those points as close as possible to the width of the stream. Then what you're going to do is divide that transect, which is your line across the stream, into equal sections, and mark it into those points where you're going to take measurements of the depth. Then you'll measure the depth at each of these points and record it on your form. And this illustration just has you taking like 3 of them, but the form that we're using has you divide it into 8 sections and then measure the depth at each of those sections. And you'll average those depth measurements. So in this example, you only took 3 measurements because you didn't have to measure at the bank where it was 0. You add them together, and because the depth at the bank is considered to be 0, you add those 3 together, divide by 4, and that will give you your average depth. So in this example, let's say that it was 1 foot at B, C, and D. Our average, including the section all the way up to the edge of the stream, is 0.75. So then you're going to multiply that by the width, and you'll get your cross-sectional area in square feet. And then what you're going to do is, you've done this twice. So you did it at your upstream transect, and you did it at your downstream transect. So you've got 2 of them. So let's say that they were different. I chose a particular example here, which just happens to match the example that I have. So let's say that at one we had 4.84 and the other one we had 6. You divide it by 2, and that's the average number that we get. And then we'll come back and use that number in our calculations. So the next measurement that we need to do is measure the travel time. And so I'm gonna share something. I'm gonna stop this share and share a short video. And hopefully it runs for you guys.
Timer ready? Start! Moving on me.
hopefully you guys were able to see that. So pretty straightforward, just timing that orange floating down the stream. All right, so with a stopwatch, you basically time how long it takes for the orange or your other object of choice to float from the upstream to the downstream. Like I mentioned, an orange is a good object to use. And the other thing to keep in mind is you want to have it in sort of the main section of the current. And you just start the time when it passes under the first transect and stop it when it passes under the downstream. And you want to do this 3 times and you'll average your results. So now you've got all the measurements that you need. And you're going to plug them back into that equation that we talked about. So in our example, the average cross-sectional area was that. That was our distance between the transects. We used that coefficient because it was a rocky bottom stream. And our time was 15 seconds on average. So if those were all the measurements that we took, then that would be the number that we end up with when you multiply it all out, 5.78 cubic feet per second. And this is what we'll do in the field on Saturday. And then as you go along, you're going to use a stream discharge worksheet. And so you'll just record each of these things as you take your measurements, plug them all in, and come up with your equation and come up with your result. So, like for instance, I did this on Little Swamp Creek this afternoon just for curiosity to see where I was at on that. And Little Swamp Creek has a whopping volume of 1.5 cubic feet per second today. So not too much, but it's just something that you can record. And if you're interested, you can compare it different times throughout the year or just year to year and think about different things that might be affecting that flow. So that's the stream discharge calculation. Pretty straightforward process, kind of fun. So now we're going to switch gears and we're going to talk about habitat assessment. And
hey, Eric.
Yeah.
When you're doing the stream flow, if you're going back to the same place, I'm assuming you'd use the same transects, but you want to measure your depth across it each time?
Yes.
I'm assuming? Okay. Okay.
Yeah, because it could change. You know, the bank could erode or, you know, something could change. So yeah, ideally you'd want to measure it, take all those measurements uniquely each time.
Okay.
And my question was, if there's any minimum width to the part of the creek that you are measuring.
I would say there's not a minimum width, but when you get to a really tiny little creek, sometimes it can be, I'll just say your result is more subject to error just because, you know, you're measuring things in like 1/10 of feet. And if your creek is only, you know, 1.5 feet across, compared to something that's 20 feet across, you know, a little error in measurement's going to kind of have a bigger effect, but there's not technically a minimum size. It's just a little bit more difficult on a really small stream.
Mm-hmm. Also, if that stream has some like reed canary grass growing through most of it, creating a flow difference, it's like right smack dab in the middle of an open stream.
Mm-hmm.
Where would you think about doing the measurement if you don't have a lot of, you know, a length that you're really, you know, unlimited amount of length to work with of the stream?
Yeah, I would probably look upstream or downstream, you know, just try to find something relatively proximate if you can that's clear. And you could use a different length. 20 feet is kind of standard, but if you only could find 10 feet, you could use a 10-foot reach. And if it's strictly reed canary grass, probably nobody will say anything if you remove some of it. Okay, any more questions?
I have a question.
Sure.
So looking at those pictures, looks like waders is a good idea for Saturday.
That is an excellent point. Yes. And so the creek that we're going to be on is North Creek is where we're going to do this training. And North Creek is about 1 to 2 feet deep there typically. So I have a set of waders. I might even have, I think my wife has a set of waders. So I might bring 2 sets of waders, a bigger set and a smaller set. But if you have them, bring them. Or if you don't mind, it's not going to be, I think it's going to be nice weather, not going to be super cold. You could always wear shorts and a pair of, Tevas or something. Or you don't have to get in the water. But it's kind of a fun thing to do. So yeah, but that's a great idea. Be prepared for however deep of water you're going to be working in. Okay, so now we're gonna move back to habitat monitoring, habitat assessment. So we're using a method that was adopted by Pierce Conservation Stream Team, and it's based on EPA protocol called Streamwalk. And what they've done is they've taken this method and they've written up a procedure and they have some check sheets. And so we're going to kind of walk through what that method is that they're using. And then we're also going to briefly touch on some methods that King County uses along with their annual BI sampling for measuring tree canopy and also measuring kind of quantifying what sort of a substrate you have in terms of size of stones and pebbles. So habitat we typically recommend you can do it annually. And I guess with any of these tools that we're providing you in this training series, you can do them as often or as infrequently as it works for you, or you can not do them if it's not something you're interested in or it doesn't work for you. But if you want to do it, we recommend you do it annually. And in terms of the habitat assessment, it's more than just the in stream, it's also the area surrounding it. So you want to pick an area around your site that encompasses a distance upstream, downstream, and off to each side. In the Streamkeeper's Guide, they recommend using 250 feet upstream and downstream. I would say you can pick whatever size works for you that's feasible. I would say if you're going to do this year to year, just be consistent in the size, the area that you pick. So before you start, you got to figure out when you want to do it. What is the size of the area that you're going to assess? Obviously, remember things like be safe, get your materials together, which in this case, there is a little bit of measurement that's done in this habitat assessment. There's some special tools, including a thing called a densiometer that is an optional thing for measuring canopy cover, and also a pebble gauge, and we'll show you some pictures of those and how they work. And then you're also going to identify like what kind of a stream are you dealing with? Is it muddy bottom? Is it rocky bottom? Are you going to do just this Pierce Conservation District technique, or are you going to use the King County Habitat Form? We typically use the King County Habitat Form in conjunction with our BI sampling when we do that. So first we'll talk about the Pierce Conservation District forms. So the first thing that they look at is just the appearance of the water. So there's lots of different ways that water might look. So you're just trying to note, does it have any funny color? Any other things that are odd looking? It's got anything floating on it? And then also, is there a weird smell? So if there's something like that, you're going to note that as well. We're also going to note the water temperature and the width of the channel. And then there's a section on this data sheet to record these different pieces of information. Next thing you're going to look at is what is the land use. And so that's something that can change from time to time. So maybe, when you started looking at the habitat in this area, maybe it was kind of rural, was relatively undeveloped. And now you have some other types of usage that's going on there. So this is where you can note what's kind of currently happening in that particular section that you're, or in and around that section that you're assessing. A useful thing to do is to sketch on the form the site. And so there's a place to do that. So you might just take your old sketch, if you started with a good sketch one year, then bring it back and you can note some changes. So that's a good way you can track changes over time as well. Like for instance, talking about land use, I live on a creek called Little Swamp Creek in Kenmore. And right now there's a construction project going on upstream of me, just out, as close to the buffer as they can get away with, of building a series of townhouses. So that would be something that I would note on my diagram that's changed from year to year. So we're going to first cover the rocky bottom assessment, and then we'll go kind of highlight some difference between the muddy bottom assessment form. So the first thing that's looked at on this assessment form is what are called attachment sites for macroinvertebrates. So these are just what sort of kind of things are in that stream, whether they're rocks, branches, logs, cobble. And then for each of these different categories, such as this one, you're going to kind of characterize it and pick a number. And this is a bit subjective, but essentially you're trying to say, okay, how well does it meet these characteristics? And, is it like optimal, or is it kind of at the bottom end of this range? Next thing you're going to look at is what's called embeddedness. So this is the idea of how much silt, sand, mud is covering the rocks, or how much are they sunk into the sand. One way you can look at this is you can pick out rocks that are on the bottom, and you can look at what percentage of the rock itself is covered. Another way you can do it is kind of look into the water and try to estimate how much of it is covered. But essentially what this means is if you have something that's more silty, then it's going to have fewer habitat spaces for macroinvertebrates and fish, and also be less suitable for spawning and egg incubation. And so again, you're going to have kind of some different descriptions for different levels of embeddedness. So your optimal situation would be you have very little embeddedness, and mostly you've got gravel, cobble, and boulders. And on the other end of the scale, you've got mostly silt and sand. Okay, then you're going to look at natural structures. So this category is called shelter for fish. So we're looking for trees, logs, branches, undercut banks, pools. Although I think we actually have a separate category for pools specifically. Sediment. So this is kind of related to embeddedness, but we're trying to characterize what is happening with how much sediment deposition are we seeing. So we're kind of looking like, okay, do we have very little sediment deposited, or do we have like heavy deposition, kind of like in this illustration here in this picture? Do we have lots of sandbars that are developing? There's more of them that are forming, lots of sediment on the bottom. So this next category, stream velocity and depth, is kind of looking at, do we have, how much variability do we have? So fast water is beneficial in some ways, slow water is beneficial in some ways, deep versus shallow water, each can be beneficial in certain ways. So you kind of want some variation in your characteristics there. So if you had like, you know, an example of something that would just be one velocity and depth, would be something that's been, say, channelized, where it's just straight and it's just a uniform channel at a certain depth, almost like a ditch, versus you have something that's very natural with fast and slow, deep and shallow. And what has happened in the creek? So has it been altered, or how natural is it? Is it running through concrete channels? Has it got riprap on the banks? Has it been straightened? Are there structures that have been built in it? This is an example in this picture of Park Creek in Bothell, which is kind of in the North Creek sports fields area. And unfortunately, it's got like some of the lowest water quality of any of the creeks in Bothell. So it's a highly altered channel. So again, we're going to have to use a scale on the form to kind of quantify, okay, where does the stream fit in this category? Is the channel filled with water, or is it dry? So like, unfortunately, right now at this time of year, and with changes that have happened in the watershed, North Creek, where it flows into McCollum Park by the Northwest Stream Center, where Adoptive Stream is headquartered, is tending to go dry, which is something that didn't happen in the past. So if you were doing a habitat assessment year to year, this is a category that you would be noting some changes on. There's some creeks that my wife and I go down to Southeast Utah sometimes, and there's some creeks, I can recall us going down to some creeks where the creek just goes dry. And, you know, I remember us on a trip one time, like rescuing fish out of these pools and putting them into deeper pools. So anyways, channel flow status is like, is the creek still have water in it, or is it dry?
So Eric,
Yeah.
on that last slide, those donuts that you see on the bottom of the creek, those are tires, I assume.
Yeah, I believe so.
Okay. A little scale.
Yeah,
Okay, thanks.
sure. Another thing is like what's happening on the banks of the stream. So what kind of natural vegetation is growing on the banks, and that will help stabilize the bank. So if you don't have a lot, if the stream bank has been exposed, then it's going to be subject to more erosion. Also, vegetation provides more habitat, like overhanging vegetation, and also provides shade, and also contributes to the food chain by dropping leaves and other things into the stream. So ideally, we want to see most of the stream bank covered by natural vegetation, but we'll just have to figure out where it fits in this, and then we'll record that score. And then also, what is the condition of the banks? So like, are they actively eroding right now? Then we're going to evaluate the riparian zone width. So the riparian zone is the area of vegetation around a stream that affects the stream. And we're talking about the natural vegetation as opposed to lawn. So like this image that I found here is an example of a non-intact riparian zone where you have grass right up to the edge of this eroded bank. The riparian zone has a huge effect on the stream. It's a buffer. It prevents things from running off into the stream. It slows water flow across the landscape. It provides shade, provides other things that like leaves and things dropping into the stream. So riparian zone is huge. So ideally you want to have a relatively intact riparian zone. So you take all these factors, and then you're gonna come up with an index score. And so ideally you would have like a reference score for like what is the best possible habitat in this area. So what you call your eco region. So essentially, like in our case, it would be like Puget Sound lowlands. So what's the best rocky bottom score we would have in the Puget Sound lowlands? And you're going to compare how you are to the best that you could get locally, and then give yourself a rating.
Eric, I have a question.
Sure.
So, what do you do if one side of the bank is like a restored riparian zone and the other side is not? How would you factor that into the equation? Like at Bear Creek.
Yeah.
We restored that whole west side of the bank. It's beautiful, but on the other side is a manicured lawn with rocks. Armored bank. So I just was wondering how you do that.
Yeah, that's a good question. And that's what I'm going to have to do some research on, because I'm not sure, how you'd score that. Because I mean, technically on one side, it's less than 20 feet. On the other side, it's great. I guess I would probably, my bias would be that if it's non-intact on one side, that you would kind of evaluate it based on the side where it's not intact. But let me do some research on that and see if I can get you a better answer.
Okay, sorry about giving a hard question.
No, that's a great question. It's a realistic question.
Thank you.
Sure. So as I mentioned, we're going to add up all our scores and then compare to what our optimal score would be, and then we'll record that, and then you would just keep this to compare your site from year to year, and it would be something that you could go back and help answer the question, is my water body getting better or worse, and why? So we'll take a look at the muddy bottom sampling form, which is mostly the same as the rocky bottom one, but it's got some differences. So some of the categories are like they've combined these two categories, shelter for fish and attachment for macroinvertebrates. They look at what's going on in the pools, how variable the pools are, and how something called channel sinuosity. So how kind of sinuous or winding is the channel. So the first category, fish, shelter for fish and attachment sites for macroinvertebrates, we kind of covered in two separate categories, but essentially we're looking at these together for the muddy bottom. In terms of the pool substrate, what's going on in the pools that are in this muddy bottom creek stream? So is it got like more gravel and sand and plants growing in it, or is it just more muddy and silty? And then what sort of pools are there? You know, are there pools? So, you know, for instance, example of the Sammamish River, there's some pools, but there's not very many pools. So that would be something that would tend to score on the low end of the scale. And then finally, the channel sinuosity characteristic. This is an example of a channel that does not have any sinuosity. And by virtue of the channel being more sinuous or having kind of more curves in it, that's going to give you differences in velocities and provide differences in habitats just because of what it does structurally to the stream. So the way that you evaluate this is you're supposed to try to estimate how much longer the stream would be if it was straightened out. So this is going to be a bit of a subjective measure, but essentially you're trying to characterize it for how much does it meet this characteristic.
Google Earth might be good for something like that.
Yeah, that's actually a great idea. So same deal. You're going to go through all the categories. I just highlighted the ones that are different, but there are some of the same categories as the rocky bottom form. And then you'll add up the score, come up with the index, compare it to what's the ideal, and rate your site, your area, compared to what's optimal. And finally, we're going to touch on some tools that you can use for measuring what they call the canopy, which is like how much do the trees overhang the stream. This thing's called a densiometer. So a canopy cover is, as I mentioned, it's how much do trees and shrubs overhang the stream. Because if the stream is shaded, it's going to both keep it cooler as well as it's going to allow more leaf litter to come into it. And there's a tool called a densiometer, which is that thing that I just showed you a picture of. And there's a procedure for measuring canopy cover using that densiometer. And essentially that densiometer is like a little mirror with a grid on it, and you cover a portion of that, and then you look into it and observe how many points are covered or not covered by reflected trees. So the first thing you're going to do is you're going to look, you're going to measure it in 3 different places. And so there's an example of a densiometer that's, you can see how it's been partially taped. So it has a grid that leaves, I believe, 17 points. So you're going to do multiple measurements in each of these different areas. So you're going to be upstream, downstream, and in the middle. You hold it at a prescribed distance above the water. And so like we have one set up where we attach some string to it and then hold it a certain distance above the water as using that string. And then you want to make it, you want to hold it so you can just barely see your own reflection in it and hold it level. And then you're going to count the amount of the crosshairs that are covered by vegetation or shaded. So for instance, if you had nothing but open sky, none of those points would be covered. But if you have nothing but tree cover, they would all be covered, or somewhere in between. So you're going to count how many that is. And then you're going to do the same thing for basically looking in 4 different directions from each of your 3 different sites that you're doing this measurement.
Eric, when you talk about this, the points that are covered, you're talking about where the lines intersect?
Yeah, the intersections.
Okay.
Yep.
Okay, thank you.
On that little grid. So as I mentioned, yeah, a stream that doesn't have any vegetation, you could have a number close to 0, whereas a completely shaded stream, you may have numbers closer to 17.
So I have a question, because the first picture you showed right before the densiometer was a bunch of trees in the winter. So how is it gonna be measured when there's no leaves? Like, do you have to, seems like that would have a big effect on your measurement.
Yeah, that's an excellent point. Typically, you're going to be doing this when the trees are leafed out. But you're right. If you did it in the middle of the wintertime or at some point when there was no leaves, that would affect your result. But it would also be interesting because you know, if you did it at 2 different times a year, let's say you did it in the summer and you did it in the winter, that would actually help you kind of characterize the canopy cover and the difference, and maybe the amount of deciduous trees are in canopy. I don't know if that would be, you know, how much that would tell you, but it would be an interesting comparison. So that's for downstream, middle, upstream, and then facing in each of the directions, and you just record the number of covered cross sections for each. So this is the King County method. The other thing that King County uses for measuring habitat is the stream sediment, and they do a thing called the Woolman pebble count. So this piece of equipment is called a gravelometer, and the idea is you are picking up rocks and putting them through those holes and counting up how many you have that fit through the different size holes. And there's kind of a randomized process for picking up rocks as you go across the stream and doing them randomly and then putting them through that, and you come up with a little bar chart. So you gather at least 100 pebbles and you pick them up one at a time, and you go, like, one way to do it is walk across the creek and pick up the first stone that your foot touches on, say, the point of your foot, whatever it is, and count that. And you call it out. So you have one person who's picking up stones and measuring them. You have another person who's recording it. And then you'll come up with a pebble count like this. And let me see if I have one. I was going to see if I have one that's filled out. So this is just describing the process. So you have one person gather and collect the pebbles. Another person records the size classes. You start on one edge. You either make a transect or you have an imaginary transect across the stream. And then you say, okay, my interval is going to be whatever it is, depending on the width of the stream. You can use the foot method that I described. Then you take that stone that you've randomly contacted or picked up, put it through the gravelometer, call out the size, and the person records it. And if it's too big to fit through any of the openings, you can measure it using the ruler portion. Measuring basically the width of that stone. And then you're going to continue doing this until you get to your count of 100 stones, 100 pebbles. And then later on, the way that your results look, so like this was Little Swamp Creek a few years ago. So you can see we did the did the densiometer count on this form, and then we also did the pebble count, and you can see by people calling it out, you end up with those tally marks. You essentially end up with like a little graph of what is the substrate like in your stream. All right, and that is it. So thank you guys for your attention. Again, those are the references we used, and also we want to thank King County Wastewater Treatment Division Waterworks Grant Program for funding our water monitoring program. So I'm going to stop recording now, and then we'll answer any more questions and talk about training on Saturday.